This is Ohm's law. It is one of the most important physics law in analyzing electrical circuits. It relates the voltage across the circuits to the current and the resistance. The formula itself is so simple that I used to often wonder about how can we actually derive it from the fundamental principles of electromagnetism. In this video, I'm going to walk through the process of deriving it by analyzing what happens in the conductor and introducing a model for it. First, we would like to take a closer look at the conductor. Assume that there are only positive charge carriers with a charge plus Q inside the conductor. Since there's a voltage across the conductor, an electric field will be generated. Let's say this electric field is pointing to the right. Then the charge carriers will feel a force and start moving to the right. Now, let's say we set off a charge counter here. It will count the number of charges flow through this cross-sectional area in a time period delta t. We will call the number of charges delta q, and we can define the current through the conductor as delta q over delta t. The question we now want to ask is that how many charges actually flow through this surface in this time. Suppose that all the charge carriers are moving with an average velocity of v. We call it the drift velocity. In this case, the last charge carrier that can pass through our charge counter should be exactly v times delta t away from the counter, because v times delta t is the distance a charge carrier can move in time delta t. So all the charge carriers before this last carrier can flow through the counter, which is to say all the carriers in this volume should be counted by our counter. Also, I want to introduce a new quantity to help us. It is n. It represents the number of charge carriers per unit volume, which is the density of the charge carriers. Now we can write the total charge passing through the counter as Q times N times volume. The volume is given by V times delta T times A, where A is the area of the cross-sectional area, so we can substitute for volume V. Remember our definition for the current. It is delta Q over delta T. And if we substitute for delta Q, we get that the current I equals to Q and VA. Lastly, I would like to introduce another quantity again. I'm sorry to do so, but I like to define a vector J, which has a magnitude of I over A, and it has a direction of where the current flows. Let's call it the current density. J will be equal to Q and V. Okay. Now we are ready to start discussing about the model and officially start to derive Ohm's law. The model is called the Drude model, named after the German physicist Paul Drude. There is a basic assumption in this model, which is that instead of moving in a straight line, the charge carriers are scattering inside the conductor due to collisions. On average, each carrier scatters once per time tau. Let's now only focus on one of the charge carriers. After each scattering, the direction of the carriers are random, but there is an electric field inside the conductor. Thus, the path of the carrier after scattering is not straight, but curved to the direction of the force exerted by the electric field. However, since the velocity of a charge carrier after scattering is random, these velocities actually cancel out each other at the end. So the only thing matters is the velocity driven by the electric field. We know that the force exerted by the electric field is given by Q times E. So the momentum P gained by the carrier after each scattering is equal to F times T, which will be Q times E times tau. Notice that the momentum also equals to M times V. So V will be equal to P over M, which becomes Q tau over M times E, where m is the mass of a charge carrier, and we actually get this v, the drift velocity, which we want. Now let's look at the definition of the current density J. If we substitute in the drift velocity v, we'll get this equation. After organizing it, we get J equals to Q squared N tau over M times E. Remember, the charge carriers in our conductor are in the electrons. The charge carried by each of them is negative E, and their mass is represented by m sub E. Since the charge carried by an electron is negative, the force exerted on the electrons by the electric field is to the opposite direction of the electric field. So the drift velocity is also to the opposite direction. we can find out that the value of this part of the equation is completely determined by the material of the conductor itself. So let's represent this whole part with sigma for simplicity. In this equation, if the electric field stays unchanged, the larger sigma is, the larger current density J will be, which is to say there will be a larger current. So it is reasonable to name the value sigma the conductivity of the material. Once again, its value is completely determined by the property of the material. Actually, this equation we gained is known as the microscopic Ohm's law, and we are almost done, only one step left. Now we want to build up a relation between the current and the voltage based on the microscopic Ohm's law we just derived. Recall that the current I equals to J times A. We can substitute J and rearrange it to get an equation for the electric field E. Also, the voltage is given by E times L, where L is the length of the conductor. Then if we substitute for E, we can include both the voltage and the current in the same equation. Now let's separate 1 over sigma from the right hand side. Notice that the larger sigma is, the smaller 1 over sigma is. Since sigma is called the conductivity, 1 over sigma is its opposite, so let's call it the resistivity and represent it by rho. Again, we'd like to treat this part of the equation together. If the voltage remains unchanged, the larger this part is, the smaller the current will be. Therefore, we shall call this part of the equation the resistance, and represent it with the letter R, and that it is. This is the equation we are looking for the entire video. It's the Ohm's law, or more precisely, the macroscopic Ohm's law. And actually, the value R we just defined is indeed how we define the resistance of the conductor. That's all for this video, thank you for watching it. If you like my video, please hit the like button and subscribe to my channel. Thanks for your support, and see you next time.